Hey guys, in this video we are going to begin our exploration of molecular geometry using a theory known as valence shell electron pair repulsion, oftentimes abbreviated VSEPR. Alright, this is quite a mouthful, sounds complicated. It turns out it's a relatively straightforward theory that is extremely powerful and useful in helping us understand the geometry for molecules. So recall, in previous lectures, we introduced this concept of a Lewis dot structure where we included bonds, shown by lines here. Right, we've got bonds and these lone pair electrons. And these structures gave us an idea of the bonding and connectivity between atoms in a molecule. Okay, but Lewis models did not tell us anything about the actual shape or geometry, right? So just knowing how atoms are connected does not tell us their exact spatial three-dimensional arrangement, okay? And this is where VSEPR comes in, or VSEPR. So the VSEPR model builds upon the Lewis model. It turns out we're going to need everything we just talked about in terms of Lewis models. Our first step in determining molecular geometry will be to build a Lewis model, follow our five-step process. And VSEPR then builds upon this model, and it uses essentially one simple fact. When you break this down, valence shell electron pair repulsion, when you're placing electrons or electron groups around a central atom, these electron groups are going to repel one another, right? Through basic Coulombic forces. You have negative charges. Negative charges want to be away from other negative charges. And this single concept is the foundation for valence shell electron pair repulsion. So looking at those valence shell electrons, and every one of those pairs, whether it's a lone pair or a bonding pair, is going to be repelled from the other groups. Okay? And it doesn't matter what sort of electron group you're dealing with, whether it's a lone pair, a single electron, multiple bonds, or single bonds. All of these electron groups are going to be resulting in repulsions. Okay? And so what valence shell electron pair repulsion theory tells us, VSEPR tells us that the geometry that molecule will adopt is the geometry that minimizes, right, these repulsions, right? So that's our whole goal here. We're minimizing repulsions, and the geometric configuration that does so is the geometry that VSEPR predicts. Okay, so one concept. Okay, so to summarize that, our method for determining molecular geometry using VSEPR is simply to minimize or provide the maximum separation, minimize the repulsion, maximize the separation between those electron groups. Okay, and the molecular geometry then depends on only two factors. One, the number of electron groups, right? The number of electron groups will determine how they're going to arrange themselves in space. And then also how many of those electron groups are bonding electrons or lone pair electrons. All right? So when we answer both of those questions, then we'll be able to build a molecular geometry. And it turns out that all of the molecular geometries that we're ever going to see for the purposes of this class fall into one of these five categories: linear, trigonal planar, tetrahedral, trigonal bipyramidal, and octahedral. Now, for our first lecture here, our introductory lecture, we're going to focus on the first three. I'm going to build up from the foundations where these come from, where the names come from, and we're going to look at some example molecules that illustrate these geometries. So let's start off by using a little simulation here, and I encourage you guys to go ahead and follow the link down here at the bottom of your lecture slides and bring up this little simulation. So if you open up the simulation found at the link in the lecture slides here, you should see an introductory screen like this. Let's go ahead and click on models first. And what this simulation does is it allows you to start off with the central atom, illustrated in purple here, and add in incrementally more bonding groups or more lone pair electrons, more electron groups, and observe the geometry, corresponding geometry that's most stable. So the first thing I want you to do is just, of course, add in one bonding group. If we put in just one bonding group here, right, it doesn't really matter. We're going to have a linear molecule no matter how you look at it, right, because there's just one bonding group. And now if we add in, however, a second atom, right, and make two bonds, now we're in a situation where these two bonding groups, the two single bonds here, are going to be repelling one another. And you can see how I'm trying to wiggle the one bond close to the other bond, but because of these electrostatic repulsions between the two electron groups, when I try and get close, the other one just moves away. And you can click Show Bond Angles down here, and it's no surprise here that the best, lowest energy configuration for these two bonding groups around the central atom is a linear configuration with a bond angle of 180 degrees. So all these atoms are all lined up. Right? You can look down that axis. They're all lined up. And anytime you try and perturb that linear arrangement, the molecule will go back to that equilibrium 180 geometry. Okay, then next what we can do is continue this process and add in a third bonding group. Okay, so if we add in a third bonding group, and we're still showing bond angles, what you see is that the most favorable from an energetic standpoint configuration is 120 degrees. 120 degrees maximizes the separation between these different bonding atoms. And once again, I can try and move these atoms in and out of the plane, closer to one of the bonds on the other side, and the system always goes back to every atom lying in a single plane, and in that plane all atoms being 120 degrees away from one another. Okay, so because all these atoms are in the plane as I illustrated here, they're all in a single plane, and if you were to connect the dots on these outer terminal atoms, it's forming a triangle. We actually call this a trigonal planar geometry. Okay? And if we continue with one more example here, we put in our fourth electron group, our fourth bond, then what ends up happening is this molecule bends into the third dimension, right? And the easiest way to, the way to maximize that separation distance between all four of these bonds is to adopt a configuration that looks like this, where every angle is 109.5 degrees away from the other bonding groups, right? And if you look at this and kind of use your imagination for a second, you can see if you kind of connected the dots here, we'd have a four-sided polyhedron or a tetrahedron that would be formed with these white atoms at vertices. And so we call this a tetrahedral geometry. Okay, so each one of these three examples, tetrahedral, trigonal planar, and linear, are simply the lowest energy configurations, maximizing the separation between these different electron groups. And these are the three different geometries that we're going to focus as we turn back to our lecture slides. Okay, so the first example that we brought up here is this idea of the linear geometry, right? Once again, we saw how linear geometries show up anytime you have two electron groups. And I want to point out that these electron groups could be single bonds, like we saw in the little simulation here, or they could be double bonds, as illustrated here with the CO2 model. Doesn't matter, we're going to have 180 degree separation in both of these cases. Okay, trigonal planar. We saw that trigonal planar geometries show up anytime that you have three bonding groups, right? So examples include BF3, right? Remember our BF3 molecule, three equivalent bonds. We've got that exception to the octet there on the boron atom. And the other example is a formaldehyde here, CH2O. Now, it's important to note here that when you're looking at a situation like this where the three different bonding groups are not equivalent, in particular we have this double bond between the carbon and oxygen, well then the bond angles aren't going to adopt that perfect 120 degree separation. that double bond has more electrons in it, twice as many electrons, so it's a bit fatter. It's going to actually occupy a little bit more space, and so the angles, the bond angles here between the oxygen and the hydrogen are actually going to be slightly larger than 120. It turns out experimentally they're about 121.9, almost 122 degrees. And then that has a corresponding effect of squishing together these hydrogens, a bit more, and they're coming in close to 116 degrees. Now, of course, I don't want you to remember exact values for these bonds for different molecules, but I want you to have that in mind, that in practice, when you don't have equivalent groups, you will often see and do often see slight deviations from these ideal bond angles. Okay, so last up here was our tetrahedral geometry. The tetrahedral geometry, as I pointed out in the simulation, basically we form this tetrahedron by connecting the dots. And a little prettier illustration right over here. That's where the name comes from. And anytime you have 4 electron groups, those electron groups are going to arrange themselves in space so that you maximize that separation distance, and you end up with something about 109.5. And of course, as the example shows here for chloromethane, if I were to switch out one of those hydrogen atoms in methane up here up top with the ideal bond angles and put in a more bulky chlorine atom, well, then what ends up happening is you get slightly larger bond angles for some of those atoms. And we can actually do some calculations and you can predict what kind of bond angle is going to occur. And sometimes you get some surprising results. So for example here, if you run calculations on this chloromethane molecule, and you could follow along there. If you have WebMO access, you'd use this sort of calculation setup, do a geometry optimization. Basically, you find that the HCH bond angle in this case is about 110.5.66, I guess, degrees, right? So this more electronegative chlorine atom is perturbing this geometry. So you're not seeing the exact 109.5, but it is close. Okay, so now the last thing we need to consider here is what influence do lone pair electrons have? Okay, so what I want to do is examine the ammonia molecule. And we're going to take a closer look at this by actually going back to our simulation. So to build up ammonia, what we need to do is we need to add in 3 bonding groups, right? And remember, if we have 3 bonding groups, right, NH3, right, then we would have just a trigonal planar geometry. However, right, ammonia has a lone pair of electrons that's right there in that central atom. So if we click on the lone pair, notice what happens here. This lone pair of electrons is serving to distort that trigonal planar geometry, and what we end up having is 4 electron groups, so we actually have an electron geometry, as it's called, that is still tetrahedral because we have 4 groups. However, if you zoom in and just look at what those atoms are doing, and what if you kind of connect the dots on all those atoms, if you will, you'll end up with a structure that kind of looks like a little pyramid here with a triangular base. The peak of the pyramid would be the purple central atom, and then the base would be formed by these 3 white atoms. And so we call this a trigonal pyramidal or pyramidal geometry. Okay? And so these lone pairs, anytime you have a lone pair, it results in us having to make this distinction between the so-called electron geometry and the molecular geometry. So electron geometry is, in many senses, kind of the easiest one. It doesn't distinguish between bonding electrons or lone pairs. All you have to do is add up the total number of groups and maximize their separation distance, right? And we know if you've got 2 of them, linear, 3 of them, trigonal planar, 4 of them, tetrahedral, and we're done. Now, the molecular geometry, for the molecular geometry, we actually have to zoom in and look at what molecules are present. Okay, so the molecular geometry depends on the actual geometrical arrangement of the atoms. which is of course influenced by the presence of the lone pair, like we saw in the simulation, right? But it is going to give rise to a different arrangement. So if there are no lone pairs present, then our job is easy. The molecular geometry is simply going to be equivalent to that electron geometry. Okay, so obviously the lone pair is influencing the geometry, significantly here. But I want to take a minute to really explore this in a bit more detail. When you have a lone pair, the magnitude of the repulsive interactions are actually different, as you might expect, when compared with a bonding pair of electrons. Okay, so if you consider the electron density, we're going to illustrate the electron density here in blue, when you have two nuclei, well, that electron density is really sort of spread out between those two nuclei. Now, if we compare that to a situation where you have a lone pair, well, then that electron density is more bunched up closer to that single nucleus where that lone pair is residing. So the result is that this lone pair is essentially a bit fatter. It's taking up more room than just a bonding pair of electrons. So as a result, if you look at the actual molecular geometry of ammonia in this case, the actual molecular geometry has slightly lower than 109.5 degree bond angles between for those H and H bonds, right? Because the lone pair, that larger, fatter lone pair, is squishing those hydrogens together more closely than we might expect. And of course, if you have two lone pairs, like in the example of water, now you're going to have an even smaller HOH bond angle. Now water's bond angle goes all the way down to about 104.5, right? Because now you have two lone pairs occupying greater regions of space. Okay, so to summarize this, methane, all groups equivalent, we get our ideal 109.5. One lone pair, smash together those hydrogens a little closer. Two lone pairs, smash them together even closer. Okay, so now we're all set with the basic foundation for understanding molecular geometry. So I just want to take a minute and go through a thorough summary of all the different geometries and configurations that we will see when we're dealing with up to 4 electron groups. So linear was our simplest case up here, the first row. If you have a linear geometry, we've got a 180 degree bond angle, right? And of course, the presence of lone pairs is essentially immaterial here because you only have two groups. It's going to be linear, of course, if you only have two atoms, okay? Okay, things got a little bit more interesting when we go to 3 electron groups, right? We saw 3 electron groups. If all of them are bonding, then we end up with an electron and molecular geometry that is trigonal planar, okay? So BF3 was the example we saw previously. Now, if you replace one of those bonding groups with a lone pair, then you end up with a situation like we'd have here for SO2, where that lone pair distorts the two bonding groups, and you end up with a structure that looks like this, and we call that a bent molecular geometry. So remember, anytime the number of bonding groups it does not equal the total number of groups, or in other words, anytime you have lone pairs, you're going to see this difference between electron geometry and molecular geometry, okay? So our final grouping here, 4, right? Tetrahedral, we know, tetrahedral if we've got no lone pairs, right? But then we saw that when you introduce one lone pair, like we saw for ammonia here on that nitrogen atom, right? Then you end up with a trigonal pyramidal geometry, molecular geometry, and then for water, when you introduce 2, we end up once again with a bent geometry. And sometimes you'll hear bent referred to as V-shape. Those are interchangeable terms. Okay, so that concludes our basic introduction to valence shell electron pair repulsion theory. The next video will cover some more advanced topics here, and we'll look at what happens if you have more than 4 electron groups.